Hello and welcome to class number 7, Hydrostatics 3, Forces on Curved Surfaces. Just a few announcements for today. I will have office hours on Friday, September 9th, today from 12 p.m. to 1 p.m. I have a commitment this morning that kept me away from class. So I'm trying something a little different, which is recording my lecture and then having Rafiq solve a problem at the end of the class period. We'll see how it goes. I want to hear your feedback, so send me an email or a message through Canvas with the good, bad, and ugly. I want to hear it all and just get your thoughts on this format. I will post this video online, so you'll be able to watch it again at your leisure if there's some things that you missed. As a reminder, homework number 3 is due Monday, and then a week from today, next Friday, there will be a hydrostatics quiz. This quiz will be 50 minutes, the whole class period, and it's closed book and notes, but you may prepare a note sheet, one side of an 8.5 by 11 piece of paper, so that you can have some equations and some materials to help you as you work through the hydrostatics quiz. So the learning objectives for this last class period on hydrostatics is that you'll be able to calculate resultant forces acting on submerged curved surfaces, and that you'll be able to determine the line of action of that resultant force on the curved surface. You're probably wondering, what the heck is that? Is all this? Well, stay tuned and you'll learn some more. So when we talk about curved surfaces, we have to figure out how this responds. So we know that we don't always have a planar surface, whether it's a vertical plane, a horizontal plane, or an inclined plane. If you go to the Living Planet Aquarium down south here in the Salt Lake Valley, you'll see that the tunnel that you walk through has a curved roof to it, and you're walking through the fish tank. So that's an application of a curved surface that you might need to figure out the force that would be acting on that curved surface to design the thickness of the glass, or to know some other strength that needs to be put into the surface that's holding the liquid back. So we can't work with the equations for planar surfaces that we've been working with for the last 2 class periods. So we have to get a little creative and do something else. We can work to determine the resultant forces using really a brute force method, which would be to integrate and get the resulting fluid force. But I'm kind of lazy. I don't like to work that hard. So we're not going to do that in this class. We could if you really wanted to, but maybe you can get an oops pass if you want to figure that out on your own. Instead, we're going to take some simple methods of action and reaction. I used the example a few class periods ago that if we press our hand down on the desk, our hand is pressing against the desk, but the desk is also pressing up against our hand. And we're going to use that concept to simplify calculations for curved surfaces. So let's talk about how we can do that. One thing to note is that we'll look at the equilibrium of the forces on horizontal and vertical projections of the curved surface. So let's talk about how we can do that. So if we consider this curved section BC in a tank that's open to the atmosphere, and when we talk about BC, that's the curved section at the bottom, we want to figure out what the resultant force is that's acting on that. So the first thing that we need to do is isolate the volume of fluid that's bounded by the surface of interest, that curved surface BC. And we want to look at the horizontal projection of that surface and the vertical projection of that surface. So let's talk about how we do that. We do that by working with a free body diagram. And so here we have a free body diagram of the area of interest, A, B, and C, because that's the piece of the puzzle that we're wanting to look at. So we just went from this big tank that's kind of tall to the curved surface portion. And when we look at this, we have the center of gravity, and that'll be important in a minute. I'll explain why. We have a force that acts in the X direction. That's the force of the water acting on the fluid. Again, if we go back, we can see this tank here, but maybe it's just a portion of a tank. And so we have a force acting, that Fx, and we have a horizontal force that acts in the opposite direction. And that represents the force of the curved surface acting on the fluid itself. We also have forces that act in the y direction. So we have gravity that works here. And so there's two components that are related to gravity. The first is the weight of the fluid, and of course that acts through the center of gravity of the surface area of interest. And then we also have a force y acting in the downward direction. And if you remember, the previous diagram had water above the this area that we're looking at in the free body diagram. And so that water that's above will act as a force. The weight of that water will act downward on this section to create the force that we need to think about for y. And then we also have the vertical force acting up against the water, and that's the surface of the container acting up against the water. When we look at the two of these things combined, the horizontal and the vertical force, we end up with the resultant force. And I'll talk about how to calculate that in a little bit. So here's some definitions. We won't spend time belaboring these because I've talked about them, but you've got them there for your notes. Okay, so let's talk about how we handle the horizontal force. So we have that drawn here. We have the horizontal force. We have Fx acting in the opposite direction, and we have to consider the vertical projection of that horizontal plane that we're looking at. Just like you considered that when you calculated the cross-section area in the inclined and vertical planes. So when we look at this and we sum the forces in the x direction, we end up with Fh is equal to Fx. And we know that we can compute Fx as the specific weight times the depth to the centroid times the cross-section area. We also know that this force acts through the center pressure of the vertical projection. So we can say that the horizontal force is equal to the distance to the centroid in that vertical projection times the cross-section area of the vertical projection. We can do the same thing when we sum the forces in the y direction. So we have to say that the forces acting down are equal to the forces acting up. So we have force of y acting from above. We have the weight of the fluid acting down, and we also have the vertical force acting in the upward direction. So we're going to set Fy plus W equal to Fv. Now looking at this a little bit more, we need to think about that location to the center of gravity. We could have a different centroid for our isolated area that we're looking at in comparison to the centroid for the composite area. And you'd have to compute that using an area weighted average. So we need to just pay attention to that if we have sort of an odd shape above the area that we're studying. Okay, now getting on to calculating the resultant force. Once we know the horizontal and vertical components, we can figure out what the magnitude is of the resultant force and then determine what that angle of action is. So we can calculate the resultant force by taking the square root of the sum of the horizontal force squared plus the vertical force squared. So pretty easy. Once you get to this step, you're in the home stretch. And then to calculate the angle of action, and this is the angle of action from the horizontal, you take the inverse tangent of the ratio of the vertical force to the horizontal force. So again, an easy number to crunch. One thing to note is that the force of the fluid on the surface is equal in magnitude and opposite in direction to the resultant force. So the two act in opposition of each other, just like my hand on the desk. Okay, so now that you've learned how to do the basic calculations, let's work an example. And because my area of research is stormwater management, I've got an example of a half-full storm drain that we're going to look at. So in this example, we have a half-full storm drain that's 3 feet in with a radius of 3 feet, and the because it's a storm drain, it's not a pressurized pipe system. The pipe's only half full. The pressure inside the pipe above the water surface is just atmospheric. There's no additional pressure head within the system. What we want to do in this case is I want you to find the magnitude of the resultant force and the angle of action of the resultant force for the water that's in a 1 foot length of pipe. And I want you to figure this out for section BC. So in this example, it's a little bit different than the schematic that we were looking at previously because we don't have water above the section ABC that we're going to look at. So the first thing we need to do is talk about assumptions. These assumptions that I'll display are things that we've talked about. I think you can probably guess what they are, but I'll just go through them quickly. So atmospheric pressure is acting on both sides of the surface. So we have atmospheric pressure acting on the outside of the pipe, the storm drain pipe, and we also have atmospheric pressure acting on the water surface inside the pipe. The water is homogeneous. We always make that assumption. And for this particular case, we're going to say that it's at rest because this is a hydrostatics problem. Now, typically water is flowing through storm drain pipes, but in this case, we'll just pretend that the water's not moving. Maybe the end of the storm drain is clogged. And then our specific weight of water is just the standard 62.4 pounds per cubic foot. All right, so looking at our solution, the first step we need to take is to draw a free body diagram. So we're going to isolate our section ABC because that's what we need to look at. We need to look at the curved surface from B to C. And what I've done is I've put the forces that are acting on this curved surface. We have the horizontal and vertical force. So that curved surface, the FH and FV are the boundary, the storm sewer pipe acting on the water inside that storm drain. We have FX acting on our body because we have that fluid that's acting in the X direction. We don't have an F sub Y, and why do you think that is? Well, it's because we don't have any fluid above the water surface. If you remember, I said that the water in the pipe was just half full. So if the pipe were full, we'd have an FY to contend with, but we don't because that water is not there. There is one thing that's missing from this free body diagram. Can you guess what it is? It's weight. I forgot to label the weight of the fluid on this. So we'll need that when we look at summing the forces in the vertical direction. So you might want to make a note of that because it is something that's missing. I've also drawn the vertical projection of the curved surface. because we know that we're going to need the distance to the centroid of that projection. And the height of that projection is 3 feet, because that's the radius of the pipe. And then our width of that projection is 1 feet. And that's because I said in the problem statement that we wanted to evaluate the force acting on the curved surface of a 1-foot section of storm drain. So now that we've talked about our free body diagram and our vertical projection, the next thing to do is to sum the forces in the x direction. I've written this so that x is positive to the right. So fx is positive, fh is negative. So we have fx minus fh is equal to 0, because we sum those forces and set them equal to 0. And then we can rearrange and say that fh, the horizontal force, is equal to fx. And we calculate fx using the specific weight of the fluid times the distance to the centroid, and that's the distance to the centroid on that vertical projection of the curved surface, and then the cross-section area of that vertical projection of the curved surface. So now we can plug in our specific weight, 62.4. The distance to the centroid is just half of 3 feet, so 1.5 feet. We have the cross-section area of that vertical projection. The area of that vertical projection is 3 feet times 1 feet. So when you plug all those numbers in and you crunch the number, you end up with 281 pounds. And that's your horizontal force. The next step is to sum the forces in the y direction. And I have a little mistake here. So if you'll look, my directional arrow points to the right. It's supposed to point up. So we're going to sum the forces in the y direction. And all we need to do here is say that FV minus W is equal to 0. And if you remember, I forgot to put the W on the diagram. So go ahead and add that into your notes. Then we just rearrange and we can say that FV is equal to W. And we get the weight of the fluid by multiplying the specific weight times the volume. And so to get the volume of the section that we're looking at, we just take pi over 4 r squared times L. And so then in the next line, we plug in our specific weight, 62.4. We have pi over 4. We have 3 feet squared times 1 foot, our length into the board. And we end up with a vertical force of 441 pounds. Now the next thing we need to do is to square each of those, the vertical and the horizontal forces, add them together, and then take the square root of those. That's exactly what we do here to end up with a resultant force of 523 pounds. The next thing we want to do is we want to get the angle of action of that resultant force from the horizontal. So we do that by taking the inverse tangent of the ratio of the vertical force to the horizontal force. So we have inverse tangent of 441 over 281. And we end up with an angle of action of 57.5 degrees from the horizontal. Now at the bottom of the slide, you can see I've drawn that value, and you can see that 57.5 degrees acting from the horizontal. Now we initially calculated that resultant force as the value that's acting against the water due to the boundary of the curved surface. But we know that the water acts also on that curved surface in equal magnitude but in opposite direction. So I've got both of those forces drawn on this diagram. I hope that this example helps you to understand some basics of doing resultant force calculations on curved surfaces. Rafik is going to give you a second example during the rest of the class period so that you can just see another example and have something live. Before we move to that, there's a few other things I want to cover just to make sure that we've got a comprehensive look at forces on curved surfaces. So the first thing I want to point out is that If we have pressure, if our fluid is under pressure, like in that mega example from class on Wednesday, we have to use piezometric head. And I have an example posted on Canvas that demonstrates how to do this. So we're not going to spend class time on it. I think you had enough of that on Wednesday in class, but I do have an example on Canvas. Another thing I just want to remind you of is it's really important that you isolate your fluid volume section appropriately, because a better selection will make the problem easier to visualize and solve. And then the last thing I want to talk about is that we have to do some things a little bit differently if there's a fluid beneath the curved surface. And let's take the next couple of slides to talk about that. So in this example here, we have a tank that has a curved surface, but you'll see that there's no fluid above the curved surface, right where the curved surface occurs. And so how the heck do we work to solve this? I'm going to just show you a few things. So when we look at this, we know that the fluid pressure tends to push it upward and to the right. And then we're going to have the force of the curved surface acting down on the fluid itself. So we have the equal and opposite forces acting there. So the way we analyze this is to create an artificial volume of fluid above the curved surface to help us calculate those forces. So this is imaginary fluid here. And basically, we use this to help us with these opposite forces. So we also know that when we look at these, we can have a fluid above and below a surface. And so here's a case of a ball that's submerged in water, and we have a force acting down on the ball. We also have a force acting up on the ball. And so this particular concept, we end up with a net force, and this is the concept of buoyant force. And anybody who's tried to put a ball in water, especially if it's full of air, you realize that the force balance ends up pushing the ball way up into the back to the surface, and that's because the weight of the displaced fluid is greater than the weight of the ball. So unless you use a bowling ball or something heavy, if the volume, the weight of the displaced volume, the weight in the ball is less than the weight of the displaced fluid, then you'll actually have the buoyant force push that object back up. And if you want to learn more about buoyancy, there's a chapter in your textbook that you can take a look at. So that's what I have for forces on curved surfaces. I'm going to turn the class back to Rafiq so that he can work an example. Hopefully you'll be able to calculate resultant forces and determine the line of action after you've worked your homework problems, and maybe listen to this lecture again. If you have any questions or concerns, don't hesitate to email me. Again, I'll be in my office hours today from 12 to 1. So I hope to see you then. Take care.